Hello, thank you for joining us today. In this short video, I'll walk you through how to interpret key performance specifications of one of our high-performance, vibration-isolated, oven-controlled crystal oscillator datasheets, the 10 MHz vibration-isolated Citrine series, OCXO. The specifications we will be looking at include the output signal, frequency stability, mechanical and dimensional information, input power requirements, frequency adjustment, the quartz crystal, performance in environmental conditions, labeling information, and test data provided with the device. From the title block, we learned that the signal source provides a 10 MHz fundamental output frequency, incorporates a 10 MHz stress-compensated crystal, is from the Citrine product line, and incorporates technology to lessen the effects of environmental vibration. The model number and revision level can be seen below the title. The first specifications seen at the top left side of the datasheet are the frequency and power level of the oscillator output signal. The output is a radio frequency signal present at the output connector when the device is under power. The signal source described in our example delivers a sine wave output of a frequency that is defined in megahertz, the number of cycles per second, and the power level is defined as the decibel level of the output signal when driving a 50 ohm load. The power level specification includes plus and minus decibel tolerance limits within which the RF signal power level is designed to remain over all environmental and tuning specifications. The next group of specifications describe various aspects of the stability of the RF output signal. The aging specification lists the daily rate of frequency change that is typical for the device after it has been under power continuously for 30 days. A crystal oscillator output signal will exhibit a slight frequency drift over time. The main source of this drift is a characteristic of the quartz crystal. The aging rate normally follows an exponential progression so that the fastest rates of change take place within the first 30 days of the unit being continuously under power. Phase noise is defined as the short-term random frequency instability of the output signal. The phase noise specification defines the maximum levels of phase noise which may be present on the fundamental frequency when measured at specific frequency offsets and at measurement bandwidths of 1 Hz. The measurement value is in decibels below the power level of the fundamental frequency. In our example, under static conditions, at 10 Hz offset from the fundamental frequency, the measured phase noise is specified to be at least 130 decibels below the power level of the fundamental frequency, written as minus 130 dBc per Hertz. In telecommunications, the fundamental frequency is also referred to as the carrier frequency. This is why power levels of signals which are being related to the power level of the fundamental frequency will be denoted by dBc, with the C meaning carrier. For oscillators designed to operate in both static and dynamic environments, phase noise specifications are listed for when the device is in a still environment and when the device is subjected to random vibration. The frequency bandwidth and power spectral density of the environmental vibration for which the oscillator is designed and tested to operate can be supplied by the customer. Temperature stability defines the maximum allowable change of the fundamental frequency due to fluctuations in the ambient temperature. The specification is written in plus and minus parts in 10 to the minus 8 of frequency change over a maximum range of ambient temperature change, referenced to plus 25 degrees C. Harmonics are unwanted signals at integer multiples of the fundamental frequency. The specification is written to define how far down, at a minimum, are the power levels, in decibels, of the harmonic signals from the power level of the fundamental frequency. Spurious signals refer to unwanted frequency components in the output signal which are not harmonically related to the fundamental frequency. The specification is written to define how far down, at a minimum, are the power levels in decibels of the spurious signals from the power level of the fundamental frequency. In our example, signals related to the power supply line are exempted from the specification. Mechanical specifications provide dimensions of the device, the input, output, and control connectors, and the material composition of the device housing. Crystal oscillators are available in a variety of packages. Depending on the product family, oscillators can be through-hole mounted onto circuit boards with pins or screws, or can be mounted to metal chassis. The dimension specification lists the width, length, height of the device in inches. More detailed dimensional information can be seen in the outline drawings located above the title block. The types and general location of the input, output, and control connectors installed onto the device are listed. In our example, the RF signal output is present on an SMA female connector, and the supply voltage, ground, and electrical tuning inputs are via solder pins. The specific location and function of the connectors can be seen on the dimensional drawings and the table located above the title block. Packaging describes the materials comprising the device housing. In our example, the case is a nickel-plated machined aluminum case. The information in the parentheses is an internal manufacturing code. Oscillators require an external regulated DC power source, typically plus 12 or plus 15 volts DC. Other input voltages may be available. The power supply must be able to supply enough power to meet the warm-up power requirement as listed on the specification sheet. Quantic Wenzel OCXOs incorporate proportional oven circuitry that adjust the power consumption in response to the environmental temperature. The warm-up power is the power required when the DC power supply is connected to the device and the internal oven is warming up. The warm-up power specification lists the maximum power in watts that the device may draw during the warm-up period as the internal circuitry heats up to operating temperature. The maximum warm-up time is specified in minutes. When the internal circuitry has reached the operating temperature, the power consumption will decrease and stabilize. The total power specification lists the maximum power in watts that the device requires to maintain the internal operating temperature when the oscillator is in a 25 degrees Celsius ambient temperature environment. The supply voltage specification lists the DC voltage required to operate the device. In our example, the supply voltage requirement is listed as being within plus or minus 5% of plus 15 volts DC. Adjustment specifications refer to the adjustability of the frequency of the output signal. Crystal oscillators with mechanical tuning feature an adjustable potentiometer, which is accessed by removing the tuning hole screw located on the device housing and is adjusted by turning the potentiometer screw with a tuning tool. The tuning hole screw should be reinstalled after tuning. The specification lists the adjustability of the output frequency in parts per million above and below the fundamental frequency. Electrical tuning refers to the ability to adjust the oscillator output fundamental frequency by applying a voltage to an electrical tuning pin. The specification lists the range of voltage which can be applied to the electrical tuning pin and the resulting minimum range of the frequency change. Often the slope of the electrical tuning will be negative, meaning the fundamental frequency will decrease as the electrical tuning voltage increases. Positive slope electrical tuning may be available on some products. Typically, the fundamental frequency is centered at the middle of the electrical tuning voltage range at time of shipment. Quantic Wenzel oscillators incorporate low noise stress compensated FC cut quartz crystals. For dynamic environments, the oscillator incorporates a low-G quartz crystal design to minimize the impact of acceleration on the frequency output. The acceleration sensitivity specification shows the maximum acceleration sensitivity of the quartz crystal and is specified as the typical frequency deviation per g-force expected in any axes, x, y, and z. Environmental specifications define the range of environmental conditions under which the oscillator is designed to operate reliably and maintain its specified performance levels. The operating temperature specification defines the range of environmental temperature, specified in degrees Celsius, within which the device is designed to maintain specified performance levels. The storage temperature specification defines the environmental temperature range within which the device can be stored unpowered without being adversely affected. The vibration level specification defines the vibration exposure a device is designed to withstand or is tested against. It encompasses the frequency range over which the vibration occurs and the power spectral density, or how the vibration energy is distributed across those frequencies. For OCXOs designed to operate in dynamic environments, the phase noise close in to the carrier will be higher than in static conditions. The dynamic phase noise limits appear on the specification sheet along with the phase noise limits under static conditions. The resonance specification informs of the natural frequency of mechanical resonance of the vibration-isolated payload inside of the oscillator. This information is useful for designers incorporating the vibration-isolated oscillator into a system. The label section of the specification sheet details the information printed on the label attached to the device. In our example, label information includes the model number, the output frequency, the product series name, the input DC voltage, and the serial number, which incorporates the date of manufacture. Test data defines the measurement data to be delivered with the device. Test data can include output level, static and dynamic phase noise, harmonic levels, spurious signal levels, power consumption during warm-up and when settled in a room temperature environment, and output frequency tuning ranges. Thank you for joining us today. To learn more about the full range of Quantic Wenzel ultra-low phase noise frequency control and timing products, including components and integrated microwave assemblies, or to discuss a custom solution engineered for your RF system, connect with us through our website or contact our sales team. We look forward to assisting you with your frequency control and timing requirements.